Hello everybody, how are you? So in this screencast, I'm going to introduce you to your new best friend called the unit circle. And as you can see at the very top of my paper, I have the words unit circle cut off just because I didn't paste correctly, completely. But the first thing I want to define for you is what a unit circle is, okay? By definition, a unit circle, and you can probably fit this up at the top of your paper, a unit circle is a circle whose radius is equal to 1 and whose center is at the origin 0, 0. And what you're going to see here is a unit circle. The x and y axes are superimposed on this, and you'll see these markings here, and you're probably wondering, what are they? Well, we're going to do a couple things, and you know what my feeling is about colors and pens, and I do think this is a wise place for you to be really careful in your notes here. If you make your unit circle and you love it so much and you'd like me to laminate it for you, guess what? I will laminate it for you. So the first thing we're going to do is we're going to go around and make angle demarcations. We're going to remember, first of all, that when we're talking about angles on the coordinate plane, that we start at standard position. So every angle always starts here at the positive x-axis, okay? And if it opens positively, right, the angles are positive. If it opens negatively, the angles are negative. So what we're going to do here is, I'm just going to go over here, and I'll call this angle theta for a minute. And the question is, what would the angle be if the terminal side of this angle terminated right here? Well, if this is the initial side, I think you can all agree this is 90 degrees, this is 45 degrees, and if you look here, this looks to be 30 degrees. So I'm going to go over here and put in 30 degrees here where the degree symbol is. And obviously, if this angle never opened, if the terminal side was right on the initial side, this would be 0 degrees. Okay? And what I'm going to do is go all the way around and put the degree measure of the angle if the terminal side of the angle were to end, for example, here. And as you see from my drawing, I'm not necessarily going to I'm not going to draw an angle for each of these. That's going to make my drawing very messy. But I hope that you will see that interesting things start to happen. Namely, what we've got going on here is this, right? It's 120. This is 135. This is 150. Now here's what I want you to do. We're going to go all the way around with the degrees, and then see this line next to it? That's going to be the radians of each angle. So for example, we know 90 degrees is the same as pi over 2. Okay, go ahead and do that and then replay me, and we will compare our respective unit circles with the degree and radian angle measures filled in. Okay, hi everyone. So here are my angles. The blue for me is the degrees, and the red is the radians. And so I'm going to repeat myself again. One of the things that I've been saying to you in class is that, I have these units here purposely picked for the end, so that we can force ourselves to become, be reviewing old content, right? So there is a method to the madness, so to speak, right? So this is kind of forcing us to be comfortable with radian measure of angles. And truth be told, you know what? You are someone, maybe you could have chosen not to pause me, and you chose merely just to copy my drawing or my information here. And that's always a choice. But you know what? It's never going to help you. It's just never a good choice to make. All right? All right. Now, what makes this unit circle so powerful is not necessarily that we kind of are able to visualize these degree measures and these radian measures. We're going to do this. I'm going to walk over here, and I'm going to pick an angle. I'll pick the 60-degree angle. Okay? And what I'm going to do is this. I'm going to superimpose a right triangle on my unit circle. Okay? And you'll notice here that if I were to really think about this and, dig a little deeper, you'll notice that really what I'm doing here is kind of taking my initial side of the angle and my terminal side of the angle. Oh dear, what just happened? I guess I can undo that. Okay, sorry everyone. And what I've done is just dropped the altitude here and made a right triangle, okay? And we know, because this circle is a unit circle, that this length here has to be 1. That is the radius. Okay, that length is 1. And we know that this angle is 60 degrees. Okay, so 1 is the hypotenuse. So now I want to ask you, if 1 is the hypotenuse of a 30, 60, 90, because if this is 60 degrees and this is 90, by necessity this has to be 30 degrees. Blast from the past. You know, you can cheat yourself out of this experience, everyone, by just listening to me and not pausing. But if you want to actually make the best use of your time, you're going to pause me here and look up, please, what the measure of this short leg, what does this length have to be if the hypotenuse is 1 and this is a 30, 60, 90 triangle, and then replay me. Okay, if you looked on your notes, you would find for the 30, 60, 90 triangle, the side opposite the 30-degree angle is always half the hypotenuse length. So this length has to be a half. And you know that the long leg, or the leg opposite the 60-degree angle, is always radical 3 times the short leg. So this long leg here is radical 3 over 2. Which then brings me to this, and here is where the unit circle becomes very powerful. Okay? If this length is 1/2, and this length is radical 3 over 2, I want you to look at this point right here, which is the point on the unit circle. What must the coordinates of that point be? If this is 1/2 and this is radical 3 over 2, doesn't this ordered pair have to be then 1/2, comma, radical 3 over 2? And do you notice now that if the angle here is 60 degrees, the x-coordinate is always the cosine of this angle, and the y-coordinate is always the sine of that angle. Okay? So there is the beauty of the unit circle, that when you superimpose a right triangle onto the unit circle, we find that these points here that fall on the circumference of the unit circle have ordered pairs such that the x-coordinate corresponds to the cosine of that angle, and the y corresponds to the sine of that angle. So take a look at this. If we're looking at 0 degrees, what is the cos of 0 and the sine of 0? It's 1 is the cos of 0, and 0 is the sine of 0. And do you see how this point 1, 0 is precisely the ordered pair right here? Go ahead and fill in the x and y coordinates of pi over 6, pi over 4, and pi over 2, and then replay me. And here's what I've got. Okay? Now you may find, if I look at my drawing here, it tends to get very congested. If you want to go back and erase this right triangle, now that you know kind of the story of the unit circle and where these ordered pairs come from, you can erase this part of the story since you already have it, right? Whatever makes this most readable to you. But what's important is that I'm noticing, I find here that these, whoops, that was supposed to be a highlighter, I'm so sorry, that those ordered pairs actually give you a whole lot of information, right? So this right here, these ordered pairs give you a lot of information. And when the radius of a circle is 1, it just so happens that the x and y coordinates correspond to the cos of that value and the sine of that value. Okay? Now, what you can do if you want to, you can go ahead and input in the rest of these x and y coordinates and then replay me. Okay, and here's what I've got. I've gone through and taken all of these ordered pairs, and I've done all this, right? And what's nice is sometimes when you think about, the cosine now of, say, 180 degrees, you have another visual to draw from. You can imagine the circle in your head and ask yourself, okay, at 180 degrees, what is the ordered pair of this point right here, because these ordered pairs of those points tell you everything you need to know about the cosine of that angle and the sine of that angle. All right, so that is the unit circle. What I also noticed in your paper is you see how up at the top here it has positive, negative, positive, negative, positive, negative, positive, negative. That's asking you in quadrant 1, for example, if it were an angle that terminates in quadrant 1, which trig ratios are positive, which trig ratios are negative. If the angle terminates in quadrant 2, which trig ratios are positive, which trig ratios are negative. You can go ahead and complete the rest of these quadrants, okay? All right, so that is it. That is the beauty of the unit circle. When you have a unit circle, what's lovely about the unit circle is that the ratios of the sides of a triangle are such that the points on the circle circumference correspond to the cosine and the sine values. And I'm now going to do, whoops, that sounded like I was about to end this. I have one more thing to show you. Do you remember our old friend, the Pythagorean identity? Specifically, that we know that the sine of an angle squared plus the cosine of an angle squared equals 1. Well, let's see why that's the case. Well, the unit circle gives us a lovely place to visualize that. If the cosine of an angle is this, and the sine of an angle is this length, as we just showed that it is, do you see how, by the Pythagorean theorem, a squared plus b squared has to equal 1 squared, the hypotenuse. This length squared plus this length squared must equal 1 squared. And now we see that when I have sine squared theta plus cosine squared theta, this is saying nothing more than the leg length squared plus the other leg length squared must equal 1. And that is a perspective on the Pythagorean theorem that I think, I forget for which section, you had a sub who tried to show you the unit circle derivation of the Pythagorean theorem. And of course, without the unit circle, you wouldn't know what they were talking about. But now you do. All right, everyone. I hope you have a wonderful night. Goodbye.